In this video, we are going to talk about separating mixtures. We're going to talk about the different techniques that are used when you separate a mixture and the physical properties that are exploited in each technique. The first thing I want to mention, though, before we get started with each of the techniques is that this is a physical separation. So when we separate a mixture, we're physically separating. There's no chemical reactions that take place. The identities of the components of the mixtures will remain the same before and after the separation. It's just that the particles are going to be farther apart, and it's going to be more like purifying the mixture and separating it into its individual components. So the first way that we can separate a mixture is by filtration. Now, the physical property that we use when we filter something is the particle size. So we're just looking at the particle size. And a lot of this will also have to do with solubility. So I'm going to put solubility in there as well, because say, for example, we have this mixture of water and sand. All right, water and sand are in this mixture together. The sand probably sank to the bottom, but one thing the sand did not do is the sand did not dissolve in the water. Sand is not soluble, or this sand is not soluble in water. So it's not going to dissolve, it's not going to form a solution. It's going to just sit at the bottom and sink to the bottom. So one thing we can do to separate the sand and the salt mixture, the sand and the water mixture, is using a filter paper and funnel. Now what a filter does is it separates out the larger particles, we'll call this the residue, from the smaller particles. The water molecules are much smaller than the salt or the sand particles, so the water can go through the funnel and the filter paper, and the sand stays behind. Now, the reason why I keep saying salt is because you can also separate a mixture of salt and sand this way. Only this time, because the salt is soluble in water, the salt will dissolve and go through the funnel with the water. The second means of separating a mixture is using distillation. And distillation relies on using the physical property of boiling point, of a component's boiling point, to separate one component from another. Say you have a mixture of ethanol and water. These are two liquids that combine and mix completely. The sand and water didn't mix very completely because the sand settled to the bottom. But ethanol and water mix perfectly. So how do we separate them? Well, we look at the boiling point of ethanol, which is 74.4 degrees Celsius. And the boiling point of water is 100 degrees Celsius. So if we heat this mixture to 74.4 degrees Celsius, which is the boiling point of ethanol, then the ethanol will boil and turn into vapor, but the water will remain in the flask that you're heating. So that ethanol vapor we can then condense or cool that vapor, turning that vapor back into a liquid and have it drip out this condenser or this cooling chamber. A lot of times condensers will have cool water running through them to cool down the vapor and turn it back into a liquid so that it doesn't just float away. You can actually capture it and use it for something. The third way that we can separate a mixture is using chromatography. Now, chromatography relies on the attraction of the particles, which really is the polarity of the particles. How polar is that particle? Does it have a very positive end and a very negative end? And the polarity is really what causes the attraction. So here we have an ink mixture on a piece of paper. In this example, it's filter paper. Now we're going to call the filter paper the stationary phase. And there are multiple different stationary phases that can be used. In this example, filter paper is our stationary phase. Then we will dip it into a solvent, which is going to be our mobile phase. And if you've ever dunked a paper towel in water, one end of the paper towel, you may have noticed that the water creeps up the paper towel through capillary action. We're going to use this technique to separate a mixture of ink colors. Now, when the solvent rises up that filter paper, that mobile phase rises up through the stationary phase, it's going to carry the pigments with it. But each pigment has a different polarity and has a different level of attraction to the filter paper. So let's take a look at this tan color. The tan color rose the highest and traveled the fastest up the filter paper. What that means is it has a very high attraction to the solvent, but it's not very attracted to the paper. If it was more attracted to the paper, it would have stuck to the paper at the bottom and it would have had a hard time going all the way to the top. So the orange color has a very high attraction to the paper, but a low attraction to the solvent. That's why the orange color kind of stuck around on the paper the longest, and it wasn't able to travel as far up that filter paper. So it has to do with the attractions of the different components to either the mobile or stationary phase. Whichever one is attracted the most to the mobile phase will travel up the highest. When we have chromatography, we can analyze our chromatograph using something called the retention factor, which really is what it sounds like. It's what is the retention of the individual component. And we look at this in terms of a ratio. So we want to take the center of the sort of oval shaped area, and what that center is that's an average. We want to know how far the average green, in this situation, the average green molecule traveled, and we're going to calculate that retention factor, the retention factor of the green molecules. So if we draw a line or put a dot in the center of that little blob there, that's going to be the average. And that distance, I'm just making up numbers here, that distance is 4 centimeters. Then what we're going to do is we're going to compare that to the solvent front, which is the total distance that the solvent traveled. And then which is 6 centimeters in this situation. Then we're just going to divide the two numbers and round it to one significant digit. I get 0.7. Now notice how the units cancel out here. So the RF value is a unitless number. It doesn't have units attached to it. Now let's take a look at the red dye. The red dye, we'll just say that it traveled 5 centimeters, so we can calculate the retention factor of the red dye. And I put a line in about halfway through so we know the average distance that a red molecule traveled, and we compare that to the total distance the solvent traveled, which is 6 centimeters. So 5 divided by 6, rounded to two significant digits, is 0.8. So the RF of the red dye is 0.8. And every molecule has its own polarity and its own attraction to the stationary phase versus the mobile phase. I want you to do the blue and the yellow ones on your own, and we'll go through the answers. So the RF of the blue dye, if the blue dye traveled 3 centimeters and the entire solvent traveled 6 centimeters, 3 divided by 6 rounded to one significant digit is 0.5. And the RF of the yellow dye, we'll say that it traveled 1 centimeter. So the RF of the yellow dye, we have 1 centimeter divided by 6 centimeters compared to the total length the solvent traveled is going to be 1 over 6. Cancel out the units for that and round it to one significant digit. We have 0.2 with no units. Now, an RF value of 1 would indicate that there is 0 attraction to the stationary phase and 100% attraction to the mobile phase. And an RF of 0 would indicate that the substance does not dissolve. There's no attraction to the mobile phase. The substance cannot dissolve in the solvent.